Okay, this is chapter 4 and the fourth class in our introduction to semantics. In this class, we will be looking at functions, arguments, and semantic types. Until now, we've laid out a general way of interpreting English expressions. We take an English expression like John smiles, and we translate it into a logical expression. That is an expression in a logical language. In this logical language, we have a predicate smile that takes in this case, one argument, John. We have then taken that and asked what it denotes, and we've given set theoretic values for the denotation. In this case, we've taken smile of John to be true if John the individual is a member of the interpretation of smile, the denotation of smile, and it's false otherwise. We've done the same thing for sentences with two-place predicates like see. John sees Mary in English translates into logic as see John Mary. And that's true if the ordered pair John Mary is a member of the denotation of see. It's false otherwise. We've so far only really asked what we want our logical expressions to look like, but we haven't really looked in detail at how we can get that logical expression, how we can derive that logical expression. And in this chapter, we're going to fill in that missing bit of information. Okay, so this box here, that's what we're going to be looking at today. How it is that we take an English expression and translate it into a logical expression. We want to do it. We want to do it piece by piece. That is, we want to give a compositional translation. We want to build up the translation of a full English expression from the translations of its parts. Some of those parts are very easy. Names, for example, are going to be straightforward. We're going to take the name John as an English name and translate it into John as a name in our predicate logic. But predicates can't work the same way. If we took the English word smiles and simply tried to translate it as the predicate logic, predicate smile, capital smile, it wouldn't tell us how to put John and smiles together. In English, those two go together into a single phrase, and we want that to translate into smile applied to John as an argument, but simply taking smile to be the predicate doesn't tell you that the smile is the function and John is its argument. It doesn't tell you how to put those together. So what we're going to do is we're going to give a more complicated way of looking at things like smile. We're going to treat them or analyze them, or as we say, formalize them, give a formal description of them as functions. The word function should be a familiar word to many of you. It's used in mathematics. And the way we use it in linguistics, in semantics in particular, is exactly the same as the way you use it in mathematics. So imagine you have a function that adds 3 to a number. We can describe that function by saying f of x equals x plus 3, right? This is an instruction, if you will, to take some number, to put it in for x, substitute it in for the x in x plus 3, and give back the result. So if you give the number 7, we have f of 7 is going to equal 7 plus 3, which equals 10. We're going to do the same thing for smile. We're going to say that smile is this function, g, that takes some x and gives back the formula, smile of x, where x is now going to be replaced by whatever argument we give to g. So if we give it the argument John, we have g of John, it's equal smile of John. Okay? So by analyzing the English word smile as a function, we derive the right formulas that we want. We don't just take the English word smile and map it onto the predicate logic predicate smile. We also now know what to do with the arguments, how to deal with John, where to put it, and how to relate it to smile inside of predicate logic. Now, functions like this are could be given as F's and G's, but in semantics, we prefer to use something that shows you a little bit more clearly what that function is. And that something is lambda calculus. It takes a little bit of time to get used to using lambdas, but once you start to see how they function, how they work, they are actually in many ways easier than using F's and G's. So in place of F, we're going to use a lambda function that is exactly the same. It's lambda x, x plus 3. Now, if you just look at the letter F, you have no idea what function it is. But if you look at the function lambda x, x plus 3, it tells you what function it is. It's the function that takes an x and gives you back the result of adding 3 to that x. So here we have that same function that's just like our f up above. And it takes a value, 7, just like f took a value 7. And the result is the same. We take that 7 here and we put it in place of the x here to get 7 plus 3. Just like we took this 7 here, put it in for this x here to get 7 plus 3. It's the same thing. Okay. Now, in the linguistic example, nothing is any different. We've changed our g now to this lambda x smile of x. This is a translation function. It takes an English expression. In particular, it takes the predicate logic interpretation of an English expression and gives back a full predicate logic formula. So if it's given, for example, the predicate logic name John, this says take that John, substitute it in place of x here inside of the expression inside of brackets, smile of x, and give back the result. And the result is smile of John. So in lambda calculus, a function is made up of lambda, a variable, here we're using x, and some bracketed expression that can contain occurrences or instances of the variable. So inside of here, we have this bracketed expression, smile of x, and it contains a single occurrence of the variable x. The other part of this is lambda conversion. When you take a function, here is a function, and you apply it to an argument, what you end up doing is substituting the argument for the variable that's bound by that function. So whatever this dot, dot, dot is here and here, that's the same thing that we have here and here. This whole thing on the left ends up being translated as something like that on the right. Okay? Now, to actually get this translation to go through, we're going to add in a translation function. It basically says, take this English expression that's between these vertical bars and give back its logical translation. okay? That is, when we put some expression E inside of here, this is the translation of E, the logical translation of E. In general, whatever is in here inside of there is an English expression. Whatever is on the right side of the equal sign is a logical expression. So let's go ahead and give a couple of examples. We have the name John. It's an English expression. And as we said before, it simply translates into the predicate logic symbol John. This is now put inside of these vertical lines, double vertical lines, to say, give the logical translation. This is the logical translation of the English word smiles, and it is equal to a function, as we saw just a little while ago. The function that takes some argument input and gives you back the smile applied to that argument. Okay, now to make use of these functions, we need something that tells us what to do when we come across them. And for that, the standard is a rule of function application. Function application tells you what to do when you have an expression that has two pieces, an A and a B. It says put them together, treating one of them as the function and one of them as the argument. So maybe A is the function term. Okay, then we take the interpretation of A and we apply it to the interpretation of B. Maybe it's B that's the function term. Okay, in that case, you take the interpretation of B and you apply it to the interpretation of A as an argument. So function application can work right to left, left to right. It doesn't really care which one is the function and which one is the argument, as long as one of them is function that can apply to the other as an argument. We can go ahead and apply this now to our simple case of John smiles. John smiles, the sentence, has two expressions. John, which is like our A above, and smiles, which is like our B from before. And in this case, it's smiles that denotes a function. John is just an individual. So we take the functional term to be the first term. We're going to take this to be the interpretation of smiles, I'm sorry, the translation of smiles applied to the translation of John. That's what the rule of function application told us to do. Okay. The next is just spelling that out. The translation of smiles we had before, we listed it, is just this, lambda x, smile of x. The translation of John is just the individual name of predicate logic, John. These we get by looking them up in the lexicon, if you will. And then we have to do our lambda conversion, which says take that John and substitute it in for that occurrence of x. We get the result, smile of John. Okay, now suppose we make the following assumptions. We assume that the name John translates as John, that the name Mary of English translates as the name Mary of predicate logic, and that the sentence, John sees Mary, gets translated as C applied to John, Mary. Okay. And we'll also assume that the sentence, John sees Mary, is structured so that sees and Mary go together as a single piece, sees Mary. We call that a verb phrase. And that John combines with that into the sentence, John sees Mary. Okay. We're also going to assume that the translation of the entire sentence is going to be given by function application. And our goal is to make use of all of this information to try to determine what the translation of the word sees has to be. Okay? So this is what we have. We have John sees Mary, and it's going to be made up of two pieces. It's got the one piece John, and the other piece sees Mary. These are our A and our B from our function application rule. And that rule tells us we can either take the A, John, and apply it to the B, sees Mary, or we can take the B, sees Mary, and apply it to the translation of the A, John. Now, in this case, only, in fact, in every case, only one of them at most will be defined. If we try the first one, taking the interpretation of John and applying it to the interpretation of sees Mary, the interpretation of John is just an individual. It's not a function. Since it's not a function, it cannot take an argument. There's nothing that it can do with an argument. And so this one is undefined. Not a problem, because we still have another option to look at. The other option, the second option here, says John sees Mary, takes sees Mary, and applies it as a function to the interpretation of John. The interpretation of John is an individual. And so this whole thing is going to be defined if and only if, that's how we read that, it's IFF, if and only if, the interpretation of sees Mary is going to be something of the following form. It's got to be a function, which means it has to be lambda x with ... in here, so that this can be seen as an instruction to replace any x's, the lambda x is instruction to replace any x's in here with John. I see I'm missing a vertical line here. There should be two of those, copy and paste error. So sees Mary applied to John is going to look like lambda x ... applied to John. And we started off with the assumption that the sentence John sees Mary as a whole translates to see John Mary. Okay? So we ask, what can the ... be so that that will be the result of applying lambda x ... to John? Well, there are two solutions that work. One is here. We fill in the ... like this. We make it lambda x, see x Mary. This is an instruction to find something as an argument. Plug that something here into that position and give back the result. We'll do that right down here. We take this as a function. We apply it to John as an argument. That John substitutes for this x, and it gives back see John Mary. See John Mary is exactly what we wanted to get. So this is a solution to the problem set up above. How do we define this so that this equality holds? It turns out there's also one other solution though, and that other solution is this. We take the lambda term to be this, lambda x, see John Mary. Now this looks kind of funny. It's like saying f of x equals 3 plus 2. There's no x over there. It's 3 plus 2. Likewise here, this is lambda x, C John Mary. There is no x anywhere in here. But it's still a well-defined term, and we can still do the same thing to evaluate it. This says, and we'll do that down here. Okay, this says find something that can substitute for any occurrences of x. Find that something here, and something is John. Substitute John for any x's you find over here. Well, there are no x's, so there's no substitution to do, but you still give back the result. And the result is C John Mary. The result is exactly what we wanted the result to be. So both of these solutions derive this equality. We end up getting them both to work as functions that can apply to John to give C John Mary. Now, there's a clear sense in which one of these is better than the other. And that's it. One of them is an interpretation that we can use anywhere. We can use it not only for the sentence John sees Mary, but also for the sentence Bill sees Mary, or the sentence Sue sees Mary, or any other sentence that has sees Mary. And it'll give us the right formula as a predicate logic translation. And the reason is because it doesn't already fix the value of x. It allows you to put anything in there that you want, okay? And here I've made a mistake. This x is supposed to be John. So can I annotate? Let me try. Okay, that's what I wanted here. I wanted John, not x. So that's here. So if that's lambda x C John Mary, that's only going to give us the right translation for the sentence John sees Mary. If we try applying that to Bill, well, there's no x to substitute for, and so Bill doesn't get in there. And Bill also then translates to see John Mary. If we apply it to Sue, the sentence Sue sees Mary also translates to see John Mary. That's not a very good interpretation for the verb phrase sees Mary. Right? Much better one is the first one. And so we have sees Mary is equal to lambda x c x Mary as our official interpretation. Okay, I think we can delete that. Now I gotta undo my, there we go. Okay, so we are halfway there. We're trying to get to the interpretation of the word sees, and now we have a good candidate interpretation, translation for sees Mary. But we do the same thing. We assume that the verb phrase sees Mary has one piece, which is a function, and another piece, which is its argument. And since Mary is not a function of any kind, it has to be the argument. So sees Mary has one part sees that translates as a function. It has another part Mary that's going to translate as the argument. And this is going to now be something of the form lambda y ... applied to Mary. Okay. We know that whatever this ... is, any occurrences of Y in there are going to be changed into Mary. And that result has to be this, lambda x cx Mary. So if we assume that this Mary here is the result of taking this Mary and replacing an occurrence of Y in here, then this ends up as this. Right? This is an instruction to find something that can substitute for Y inside of here. If that something is Mary, then Mary substitutes in place of Y. If we do that, then the result is exactly what we want, lambda x cx Mary. And so we've derived a meaning for C's. C's, the translation of C's is lambda y, lambda x, cxy. Okay, we will show that that gives us the right results by using that meaning in calculating the translation of the sentence, John sees Mary. Okay, so we start with the assumptions that the name John translates as John, the name Mary translates as Mary, and then the word sees translates as what we just calculated. It translates as lambda y, lambda x, cxy. We can do the calculation in two ways. One is bottom up. Bottom up means you start at the bottom of a tree. You start with the individual words and you combine them. And you get a result, and you combine that result with the next thing. And you get a result, and you combine it with the next thing, and you go all the way to the top. Okay? In that case, we start at the bottom. We start with putting the word sees and the word Mary together. We get sees applied to Mary. The translation of sees is here. The translation of Mary is here. We take the Mary, we substitute it in for this occurrence of Y, and we give back the result, and the result is lambda x cx Mary. To finish off the derivation, we take that result, the interpretation of sees Mary, to combine with the translation of John. That is, we take a translation of sees Mary, apply it to the translation of John. We just calculated the translation of sees Mary to be this. We have the assumption, the interpretation of John is John. We take this John, we substitute it in place of this X, and we give back the result of the substitution, which is C, John, Mary. Okay? So next we're going to do basically the same thing, but this time we're going to start at the top of the tree. We're going to start with John sees Mary. So the sentence John sees Mary has two pieces. It has John as its first piece, and it has sees Mary as its second piece. One has to be the function, the other has to be the argument, and you have to guess. But since you know that John is going to be an individual, it's not a function, we can guess that sees Mary is the argument. So we say this is going to be sees Mary applied to the translation of John. Next, we go ahead and calculate the translation of sees Mary. That is going to be broken into, again, two pieces. The translation of sees as a function applied to the translation of Mary as its argument. This part here, that we take that result applying it to John, that stays. We don't change anything there. Okay. And now we've gotten to our basic pieces. We can't go any further by splitting things into two. And we look up here. We find our interpretations here of the name John, of the name Mary, and of the word sees, and we just plug those in. This is the translation of the word sees. This is the translation of the word Mary. This is the translation of the word John. Okay, and now we go ahead and we do our lambda conversion. We do it left to right. We take this function and we apply it first to this argument. That tells us to take the word Mary and substitute it in for y. Give back the result. That result is here, lambda x cx Mary. This is again a function, and since it's a function, it can again apply to an argument. It applies to the argument John. John goes in place of x, and we get back C John Mary. Okay, so these two different ways of doing the calculation, top down, bottom up, they both give the exact same results. In longer derivations, you can work from the middle out, middle to the top, and then go back and go from the middle to the bottom. You can combine things in any order you want. The results should always come out the same. Okay, so far we've been only assuming a very, very minimal syntax. And we're going to stick to fairly minimal syntax assumptions for the rest of this book. In particular, we're only going to put in as much structure as we really need most of the time. And this is the only structure that we actually need for a sentence like John smiles. It has to have some one node, we call it an S, it doesn't need a label, that has two daughters, John and Smiles. Then when we try to interpret the whole thing, we do that by combining the translation of one of the daughters, Smiles, with the translation of the other daughter, John. Incidentally, this kinship terminology, mother and daughter, is very commonly used in syntax. Here, S is the mother node of the tree. John is one of the daughter nodes of S. Smiles is another daughter node of S. And Smiles and John, these two are sister nodes because they are at the same level. Neither one dominates the other, but they both share the same mother. Okay, so that's the minimum that we need for doing our semantics, but there's a very unrealistic assumption in syntax. So depending on what era you look at in syntax, people have added various other things to these structures. So for example, instead of just putting the name John by itself, people will assume that John is itself a noun, which is a very simple version of a noun phrase. The word smiles itself is a verb, and in this case, the verb by itself counts as a verb phrase. Okay, well, we don't yet have a way of interpreting this because we don't know what to do with these verb phrase VP dominating a V, dominating a single daughter Smiles. Even more complex structures have been given in syntax. We have the noun phrase dominating the noun dominating John here, but instead of just a verb phrase, people have said we have an auxiliary phrase. That auxiliary will have some phrase will have an auxiliary element, which will include tense, as well as some forms of be and forms of have in certain sentences, but not this one. Okay, so pres is present tense. And we certainly want to say something about how tense gets into structure, into a language. And this is one way to analyze that. And we haven't said anything about what to do about these structures. We can, however, look at that and say this is just like here we have a single sentence. I can't do it. Okay, we have a sentence dominating an NP and a VP. It's one node dominating two others, right? Here we have one node dominating two others. If one of these two others is a function that can apply to the other as an argument, then we can go ahead and calculate this by function application. Okay. Now I've drawn these out as syntactic trees up above, but very often we also use an equivalent way of representing those trees. That's here. It's called the labeled bracket representation. But it contains all the same information. We have at the outside a sentence. And it's bracketed to show what it dominates. That sentence dominates two pieces. One piece is an NP, that's this piece. One piece is a VP, that's this piece. Okay, and the NP itself dominates a noun, and that noun dominates John. The NP itself dominates a noun, which itself dominates John. And similarly for the VP. The VP here dominates the verb, which itself dominates smiles. Okay, and similarly for this longer one here, longer one that I can't seem to highlight the whole thing of, this whole thing. Okay. Sometimes I'll be using one representation, sometimes I'll use the other. So you should get familiar with both of the representations. Okay. Another thing that is very common in syntax is to assume that there is some kind of movement involved in generating structures. And I've represented that here by having a trace, T sub I, of the noun phrase NP sub I. So the idea is that this noun phrase John starts out in some way here. It combines with smiles to form a VP. That VP combines with, say, tense, present tense. This could have been an auxiliary. It could have been tense. People have made different assumptions. To produce a intermediate projection, tense bar, T bar, which now we take the John that used to be in the trace position and we raise it to here and combine it with this T bar to get a TP, a tense phrase. Okay, so these are the kinds of structures that are more realistic, more and more as they go along. This is the most realistic structure. In this class, however, we're not going to be dealing with movement. To analyze movement is an advanced topic. We'll save that for an advanced semantics class. So we will at most be using structures like the one dominated by this S. And more commonly, we'll be using the simpler structure. Here, the one on the left, this structure. And the choice is out of what do we need to do. At some point, we're going to start analyzing tenses. I believe that's chapter 8. At that point, we need to make sure that the tense is somewhere in the structure. And at that point, then we use this structure, the one on the right. Until then, when we're not looking at tense, we can ignore it. The easiest way to ignore it is to just adopt a structure that doesn't have it. In a structure like, I just can't, like the one on the left. Okay. Now, I said we have these extra little bits of structure that we don't know how to interpret yet. They're bits of structure that either have an X dominating a Y in a syntactic tree, or a labeled bracket X containing nothing but Y. Okay? These are two different ways of representing the same thing. And the way we're going to do the translation is very simple. If a node X dominates a single daughter node Y, then the logical translation of the whole is equal to the logical translation of Y. That's given here. The logical translation of entire structure here, the interpretation of an X dominating a Y is equal to the interpretation of Y. Okay, so we have all of the pieces that we need for doing our very simple sentences. And if all we had to worry about are simple sentences, we could probably just stop there, give different meanings and show how they combine. But when we start looking at more complicated structures, it gets very hard to see what a meaning should be for an expression inside of it. And so one of the things we do to kind of help ourselves figure out what kind of a meaning something should have is we divide expressions into types. The types are based on the kind of denotation that an expression has. So expressions that have the same kind of denotation are of the same semantic type. The names Mary, John, Bill, and Sue, for example, are all of the same semantic type. Each denotes an individual. The sentences John smiled and John didn't smile are also of the same semantic type. Each denotes a truth value. The predicates smile and sit are of the same semantic type. Each denotes a function that takes an individual and gives back a truth value. Okay. And we're going to define types recursively, and I'll tell you what that means in a minute, as follows. We're going to take there to be two basic types. Those basic types are E and T. E is a type, it's a type of an entity. Entity is just a fancy word for object or individual. Okay. T is a type. It's a type for truth value. There are only two truth values, true and false, where their type is T. The next one is where the recursive definition comes in. It says if sigma and tau are types, then bracket sigma comma tau bracket using angle brackets is also a type. And its denotation is a function that takes sigma type things and gives back tau type things. Okay? So let's take a look at examples, our simple examples. Simples are good for illustration. The name John denotes an individual, that's an entity. John is of type E. The sentence, John smiles, it's either true or false. It has a truth value. Truth value means type T. And finally, smile is a function that takes an individual, like John, and gives back a truth value, like the truth value of John smiles. It's a function that takes an individual and gives back a truth value. Its type is E, comma, T. I usually don't read the comma, so this is we called type ET. Okay, I'm sorry, I said I was going to get to what recursive is. So the notion of recursive is a recursive definition defines, in this case, a one type based on other types. That is, if you will, you can think of the definition of saying put A and B together into C, where C can then act just like A and go together with something else in the same way. So just like we can take E and T and put them together into type ET, we can also take that same ET that we just produced and put it together with E to get a type like ETE. ETE was not what I wanted here. ETT is what I wanted here for the type of everyone. So pretend that this is the letter T. It only matters because I've chosen to say that this is an illustration of the interpretation of everyone. And everyone does not denote an individual and does not give us a function that gets to an individual. So that's a mistake. But so these are still types that are kinds that we would maybe use in semantics. And I can see I've made a lot of mistakes on this slide. I apologize. ETE is actually the type of the word the. EEET, that's the type of the word show. That one I got right. ETET would be the type of the word very, among other things. So many of these complicated types we will use in semantics, but there are also very many that are not usually used. I've given 3 examples here. These are types that we can generate using our rule of types. It says anytime we have 2 types, 2 things that are types, like T and E, we can put them together and to create a new type, type TE. And we can take that and put it together with something else that is a type, like E, to create a type ETE. Yes, we can do that. But it seems like English, and maybe all natural languages, don't have any use for those types. We can create an infinite number of them, but we only use a very small number of them. Okay. Now we can indicate the types directly in the syntax. We do that by taking a label like S, putting a colon, and after the colon, we give something semantic, in this case, a type. The sentence is something true or false, it's of type T. John denotes the individual John. That's an entity, an individual. It's of type E. The interpretation of the noun is the same as the interpretation of John, so it's also going to be type E. The interpretation of the NP is the same as the interpretation of the noun, so it's going to have this same type as well, type E. Similarly, for smiles, smiles is a function of type ET, so the verb and the verb phrase are also of type ET. Now, the important thing to keep in mind is how these two go together to make this. This is a function. It takes something of type E as an argument, and this is going to be that something. This is the type E. Okay. It takes that type E and it gives back the type T. That T is this one. So this ET type is a function that takes an E-type expression and gives back a T-type expression. If the types start to work out properly in semantics, they always have to have this character. One of the types has to be a function that can combine with the other type as its argument to yield what that function gives you. Now, we can use partial information about types to calculate the types for other expressions that we might not know. So suppose that we didn't know yet what the meaning of sees was. But we knew that the sentence, John sees Mary, is a sentence. As a sentence, it's either true or false. Its type is T. And we know that John is an individual. His type is E. Mary is an individual of type E as well. Okay. We can use that information to calculate what the VP has to be, what the V has to be, and what the C's has to be. In particular, what types they have to be. In order to combine these by function application, one needs to be a function and the other its argument. E is the type of an individual, not of a function. Functions have angled brackets with two pieces. E doesn't have angle brackets and it doesn't have two pieces. So VP has to give us the function, and it has to be a function that takes this E type thing and gives back a T type thing. So we can tell that the verb phrase type is going to have to be this, ET, in order for this to be a well-formed sentence. Okay. If we look only here and ignore the VP for a minute, we can get partial information about the verb, what kind of type, what type it has. We know that it has to be able to take an E-type expression as its argument and give back something else. That is, the verb is going to have to be a function from E to something else. And we also know that that something else is going to be the type of the verb phrase. It's whatever this question mark is. Right? Well, we've already seen what that is. We've calculated it to be the type ET. And so we can take this and replace it by that ET. And we get the type for the entire verb. It's type EET. That is, just starting off with the information that we have here on the tree structure, we can determine all of the types of the expressions in the tree. We can use this for giving types for words, other words as well. So imagine that you have the following assumptions. The word cat is a one-place predicate. It's true of things that are cats and it's false of things that are not. So it's a function that takes a thing and gives back a truth value. Okay, its type is ET. And suppose you decide that the expression the cat itself is of type E. It's like a name, it picks out an individual. Okay. Now, you might have a reason for thinking that those are bad choices to make, but if those are the assumptions you make, then you can calculate the type of the, like this. Here we have an ET. That's something that requires an E and gives back a T. If we put E here, that would mean this NP as a whole would have to be T, type T. But we started with the assumption that it isn't, that it's of type E instead. And that means we can't take cat to be the functional thing that takes this as its argument. Rather, we need the to be the functional thing that takes cat as its argument. That is, the requires an expression of type ET, that's cat, and it gives back something that's of type E, that's the cat. Of course, this doesn't tell us exactly what the means. We'll get there in another 2 chapters, but it tells us at least what kind of a thing the is, okay? What kind of an expression we should be looking for. So quite generally, suppose we have an expression that has an X as a mother node and Y and Z as daughter nodes, either order, Y before Z, Z before Y, okay? And suppose that the X we already know has a type tau. And the Y is a functional node. It has a type sigma tau. What is the interpretation? What is the type of Z? What kind of an interpretation does it have? Well, there are 2 solutions. In this very particular case, there are 2 solutions that will work. So this is a function, Y is a function that requires a sigma and gives back a tau. And this is a tau. So the easiest solution is for this to be of type sigma, right? That's Y is acting as a function, applying to Z of type sigma to give back an X of type tau. But we can also switch things around, and this will come up again in probably 2 chapters. Z could itself instead be the function that takes this kind of a thing, this type of a thing as its argument, and gives back this type of a thing as its value. In that case, the type of Z is this. It takes a sigma tau function, gives back a tau type argument. So these are the 2 general solutions that we have for trees that have this particular pattern of types, where this is a function from one type sigma to some other type tau, and the mother node itself is of type tau. Okay, that's it for this week. We will do more of these lambda functions in more detail next week. I should give you a warning now. Lambda functions cause many people difficulties. It's a very mathematical concept, and you have to use them very precisely in the way they're defined. I will give you exercises for practicing, but it's very easy to make mistakes. So practice until you get comfortable with them. Okay? Okay, I will see you next time.